Good afternoon, all of you. Today we will discuss about problems on DC machines. So mostly on DC motors. First problem. So a DC shunt machine connected to a 250 volt supply. So first open the problem and draw the circuit. A DC shunt machine connected to 250 volt supply has an armature resistance including brushes is 12.12 ohms and the resistance of the field circuit is 100 ohms. Find the ratio of the speed as a generator to the motor as a motor. The line current in each case is 18 amperes. Line current in each case is 18 amperes. So same circuit. First time machine act as a generator. Second time the machine act as a motor. So first draw the circuit diagram. So this is a shunt machine. So shunt machine is armature and field both are connected in a parallel. So this is the armature, shunt, field winding, armature winding, both are connected in parallel. So this is the supply voltage. First we take a generator, which act as a generator. So 250 volt supply. 250 volt supply voltage. So shunt machine is armature and field both are connected in parallel. So first machine act as a generator. Take this as a generator. The generator means current delivers. So the line current in each case is 80 amperes. So first generator delivers 80 amperes of current. So this is the line current of the generator. So in any case, maybe generator or motor, in both cases, machine takes a field current. So that is ISH or shunt current or field current. So now we need to calculate ISH shunt current. So shunt machine means both are in parallel. So the same supply voltage, the generated voltage or terminal voltage is same for both cases. So that is shunt winding and armature winding. So this 250 volts is same for field winding and armature winding. It is connected across. Across means voltage is same. So this terminals. So we know the voltage and the resistance of the field winding. Then we calculate the shunt current. Current equal to voltage by resistance, because we know that V equal to IR. Ohm's law. In DC circuits, V equal to IR. Therefore, I equal to V by R. I equal to V by R. So therefore, I equal to V by R. So voltage 250. Shunt resistance is given. Resistance of the shunt field winding is 100 ohms. Shunt winding 100 ohms. So 250 by 100, that is 2.5 amperes current is the shunt field current. So that means this current is equal to this one, shunt field current. So here shunt current equal to 2.5 amperes. Shunt current equal to 2.5 amperes. So this line current equal to 80 amperes. Therefore, this armature delivers, because it is a generator. So generator's delivering current equal to 82.5 amperes. So armature current of the generator is 82.5 amperes. So 80 plus 2.5, 80 plus 2.5, 82.5. So armature delivers 82.5 amperes of current. So this is 82.5, 82.5 amperes of current. So generated EMF equal, therefore EG, generated EMF is across the armature, EG. So this EG value, generated EMF EG or E1 equal to V plus IR. So in case of generator, EG equal to V plus IR. So this is the generated EMF equal to terminal voltage plus IA RE. IA means IA1, first case 1. So generator case IA1. So this is the EG1, IA1, RA. Armature resistance is same. So 250 into 2.5 resistance. This is the total voltage, generated voltage of the generator. Now in case of motor, so the circuit becomes reverse. In case of motor, the circuit becomes reverse. So this is the motor. Shunt motor. In shunt motor, current machine takes current. So in case of motor, machine takes current. So current direction, line current direction reverses just simply line current direction is same current. Machine takes same current, but it takes current. In case of generator, it delivers the current. In case of motor, it takes current. So from 80 amperes, shunt current is same because voltage is same, 250 volts. Terminal voltage is same. So shunt current is 2.5 amperes. Therefore, armature current of the motor, that is IA2. So 80 is incoming current, 2.5 outgoing. So this remaining current is 77.5. 80 minus 2.5. So that is 77.25. 77.25. So this is 77.5 amperes takes the current of the armature of the motor. Motor armature current 77.5 amperes. So in case of motor, see, line armature current equal to line current minus shunt current, because motor takes line current. So from that we subtract the shunt current. Same, 80 amperes is the incoming current. So minus 2.5 is the shunt current. 80 minus 2.5. 80 minus 2.5. So 77. Armature takes 77.5 amperes. So in case of motor, back EMF equal to, so back EMF is nothing but generator EMF in motor. So back EMF equal to V minus IARA. In case of generator, generator EMF is V plus IARA. Here plus, here minus. So motor case V minus IARA. Generator case V plus IARA. So second case kabatti generator EMF, back EMF E2, IA2, RE. Because only armature current changes. Voltage and resistance are same. So 250 minus IA2 value is 77.5, resistance value. So 240 volts is the generated EMF or back EMF of the motor. Back EMF of the motor. So this is for motor, this is for generator. So we know that in any case it may be motor or generator. Speed is proportional to back EMF and inversely proportional to flux. In case of generator or motor, speed is in proportional to back EMF, inversely proportional to flux. So N is proportional to back EMF or generated EMF in motor and by flux. So this is a shunt machine. Shunt current is constant. Constant shunt current means field flux is also constant. If not given, field flux is also. There is no change in flux. So flux is constant. So flux is same. See, in both cases flux is same. So speed is proportional to back EMF only. Back EMF or generated EMF. So N1 by N2 equal to EB1 by EB2. And that is N1 by N2 equal to E1 by E2. So in this manner, we calculate the speed ratios. So we need to calculate the speed as a generator, speed as a motor. So generator speed by motor speed is N1 by N2. So this is the ratio of the speeds in the given problem. Ratios of this. So this is problem number 1. Now the second problem. The armature resistance of a 250 volt shunt motor. 250 volt shunt motor is 0.4 volts. And no load current is 2 amperes. No load current is 2 amperes. When loaded and taking an armature current of 50 amperes, the load current. So loaded and taking armature current. So no load current is no load armature current is 2 amperes, and loaded the armature takes 50 amperes. The speed is 1200 rpm. Speed is 1200 rpm. Find approximate no load speed. Find approximate no load speed. So case 1, first case at no load. So it's a motor, shunt motor. Motor means V minus IRA. So no load is represented with the NOT. So this back EMF equal to V minus IRA. So no load case, so that's why we represent with NOT. E naught equal to V minus no load current R. So terminal voltage 200 volts. 200 minus no load current 2 amperes and a resistance. So this is a no load back EMF. This is a no load back EMF. So under loaded condition, back EMF equal to E1. So this is load case. So first case no load. No load. So this is the load case. Second case load. Load case. Back EMF voltage is same. Supply voltage or terminal voltage is same. So loaded current 50 amperes. IA1 is the 50. This resistance is also same. So 180 volts is the back EMF at loaded condition. Back EMF at the loaded condition. So this is the load. First case is the no load case. So we know that speed is proportional to back EMF by flux. EB by flux. So EB by flux. So back EMF by flux. Find the approximate no load speed. We need to calculate approximate no load speed. So this is the shunt machine. There is no change is given in flux. So flux is also constant here. Flux constant means N1 by N2 equal to EB1 by EB2. So we need to calculate the no load speed. That is the no load speed means N0 by load speed N1 equal to no load back EMF, that is E0 by E1 loaded back EMF E1. So from this we calculate the no load speed. No load speed, that is this one. 1328 is the no load speed of the motor. In this manner, we can only we take constant flux because the flux change is not given. There is no rheostat in the shunt field winding, and flux change is also not given. That means flux is constant in two cases. So phi1 equal to phi2. So this is a very important formula for speed control. Important. N is proportional to back EMF flux. Because back EMF equal to pi Zn by 60 into P by A. Back EMF equal to pi Zn by 60 into P by A. So this is also very important formula for calculating the speed in terms of back EMF. So this equation is obtained from back EMF of the generator. Back EMF is nothing but generated EMF, EG, generated EMF in the motor. EG equal to pi Zn by 60 into P by A. So for a given machine, pulse is constant, band pass is constant, 60 is constant, conductors is also constant. So that means back EMF equal to some constant into EB equal to some constant into flux into speed. Flux into speed. So speed is proportional to back EMF by flux. So from this we calculate this value. This is the speed is proportional to back EMF by flux. So the flux is also constant. So because shunt machine, flux is constant. N1 by N2 equal to EB1 by EB2. In this manner we calculate the speeds. So this is problem number 2. So therefore we go next problem. Next problem number 3. Same problem, but values are different. No load current 2 amperes. In last case, Same problem. Same problem. Next this one. Good 50 volts shunt motor having an armature resistance of 0.25 ohms. 0.25 ohms carries an armature current of 50 amperes and runs at 750 rpm. The flux is reduced by 10%. Flux is reduced by 10%. Find the speed. Assume that load torque remains same. Assume that load torque remains same. Shunt machine, here also shunt machine. So here the 250 volts input supply having armature resistance 0.25 and armature current 50 amperes. So motor means it takes current. So the 50 amperes is the current taken by the motor and runs at 750 rpm. Flux is reduced by 10%. Find the speed. So first initial condition and the initial condition depends on the initial condition. So V is 250. Armature current IA1 first one 50 amperes is given. Resistance is same 0.25. Speed N1 750 rpm. So EB1 back EMF in first case EB1 equal to E minus IA1 RE. So 250 volts minus 50 into 0.25. So 237.5 is the EB1 first case back EMF. So condition given is flux is reduced by 10%. Flux is reduced by 10%. Initial flux, for example, initial flux 5.1. So initial flux is the 5.1. We assume that initial flux is 5.1. So second flux 5.2. 5.2 equal to reduced by 10%. That is 0.9 into 0.9 into 5.1. 0.9 into 5.1. So 90%. So 0.9 into 5.1 means 90%. Initially we have 100% flux. Flux is reduced by 10% means we have 90% flux only. That is 1%. 0.1% is reduced. 10% means 0.1. 0.1 reduces times 0.1 times reduces. So new flux value, this one is the new flux value. I2 equal to 0.9 into 5. So we know that our armature torque is equal to armature torque is given by some constant into flux into armature current I. So I armature current. So torque remains same and T1 equal to T2. So that means 5.1 IA1 equal to 5.2 IA2. The torque is same. Torque is same means torque is proportional to flux and armature current. So therefore 5.1 into IA1 equal to 5.2 into IA. So this is the formula because torque is remains constant given condition. On the given condition, torque remains constant. So from this we calculate the IA2 value. So IA2 value. IA2 equal to 5.1 by 5.2 into IA1. So you substitute the relation and then we calculate the current. So that is 55.56 is the new armature. And then you calculate the back EMF. After calculating the current, calculate the back EMF. So this is the back EMF value. Second case, the final condition. So same, because we know that speed is proportional to back EMF by flux. Last problems, back EMF flux. So therefore, N1 by N2 or N2 by N1 equal to EB2 by EB1 into 5.1 by 5.2. This is the relation. So this is the relation. From this relation, we calculate the speed. 828.5. Initial speed is 750. Second speed is 828.5. So this is the second problem. In conditions, given conditions are flux is reduced by 10% and torque remains same. If torque remains not same, not given, take the assumption torque remains same. So this is the problem based on series motor, DC series motor. This problem is based on DC series motor. Okay, 250, 240 volts DC series motor takes 40 amperes. When giving its rated output, when giving its rated output at 1500 rpm, at 1500. So rated output at 1500 rpm. Its resistance is 0.3 ohms. Resistance is 0.3 ohms. Calculate the value of resistance that must be added to obtain the rated torque condition. First case at starting and at 1000. What is the resistance that must be added in series with the circuit? Because series motor means armature and field both are connected in series. In addition to armature resistance and series field resistance, we have to add some external resistance to change the torque. To change the resistance must be added to obtain the rated torque at starting as well as at 1000 rpm. At 1000 rpm. Starting torque and at 1000 rpm torque is the same. So case 1, solution. So voltage equal to 240 given, current value 40 amperes, N1 equal to 1500 rpm, speed, initial speed, the rated output is at 1500 rpm, and armature resistance 0.3 ohms. So back EMF is calculated, back EMF equal to V minus IRA, because series field resistance is not given. You see here total resistance is 0.3, series field and shunt field. Because this is the circuit diagram here. Armature and shunt field. So this is the series motor diagram. Shunt field total resistance is given, series field resistance and armature resistance. Total resistance is 0.3. So therefore back EMF equal to only V minus IRA. If series field resistance is also given, field resistance is also given, back EMF equal to V minus I into RA plus R series. If series resistance is not given, that is the total resistance, that is equal to V minus IA RA. So voltage value 250, current value 40 amperes, and armature resistance 0.3. So therefore back EMF equal to 228 volts. So this is the conditions at the rated output. This condition is at rated output. Now at the starting means at the time of switching on the motor. At the time of the switching on the motor means speed equal to 0. At the time of the switching on the motor means speed equal to 0. So therefore back EMF is also equal to 0. Why back EMF is 0 at the starting means at the starting time speed equal to 0. The motor started with the starting speed equal to 0. So this is the condition. So speed 0 means back EMF depends upon speed. Back EMF equal to Z 10 by 60 into P by A. Because back EMF, we know that back EMF equal to already written last column I Z N by 60 into P by A. So speed 0. So speed 0 means it's back EMF or E. Value is also equal to 0. The speed 0. So this is equal to V minus. So in order to obtain the rated torque at a rated current, an additional resistance R1 is added. R1 is added in series with circuit. So additional resistance is added here. Additional resistance is added here. So this is the very additional resistance R1. Now the back EMF equal to V minus IA into initial resistance RA plus additional resistance R. Back EMF equal to 0. Voltage, terminal voltage 240 minus rated armature rated current to 40 amperes. Same 40.3 R. So therefore R1 equal to 5.7. If you add a external resistance 5.7 ohms in series with the armature, then we get rated starting torque. Rated starting torque at 1000 rpm. At case 2 at 1000 rpm. So at 1000 rpm means back EMF will exist. So back EMF at 1000 rpm equal to this one, equal to V minus IA RA plus R2. What is the resistance that must be added in series of the motor is R2. First case R1, second case R2. This is R1, this is R2. Here back EMF will exist because at 1000 rpm. 1000 rpm means speed will exist, therefore back EMF will exist. Equal to this one. So here same condition. So speed is proportional to back EMF by flux. Back EMF by flux. So back EMF by flux. So from this, so this is the initial condition. N1 5 E2, N2 5 2 E2 is the third case, that is this one. So armature current is same, that is IA equal IA2 because of rated current. So the armature current is same, means series motor lo armature current and field current is also same because armature current is proportional to flux because of both armature and field are connected in series. So armature current is same as field current. So field current armature is same, means same current means fluxes is also same. Okay, so IA2 is replaced with IA. So on the same currents means that is cancelled. That is N2 by N equal to E2 by E because currents are cancelled each other. From this we calculate R2. By substituting this equation, we calculate R2 value. R2 equal to 1.933. So in this manner, we calculate the external resistance in series with the armature circuit to get the rated torque at starting as well as at 1000 rpm. So this problem is based on series motor. Now the next problem. Here also series motor with unsaturated magnetic circuit and 0.5 ohms resistance. When running at a certain speed, takes 60 amperes at 500 volts. If the load torque varies as the cube of the speed, torque varies as the cube of the speed. Calculate the resistance required to reduce the speed by 25%. Calculate the resistance required to reduce the speed by 25%. So read the problem carefully. Torque is proportional to N cube given. Torque is proportional to N cube. So here back EMF is calculated first here. Back EMF will be minus IRA 500 minus 60 amperes. Resistance 0.5 is the force only the back EMF. Speed is reduced by 25% and initial speed N1. So N1 is the initial speed. N2 equal to 25% is reduced. So that means 100 minus 25. That is 0.75. 0.75 into, so this is given. So torque is proportional to N cube given. So T2 by T1 equal to N2 by N1 whole cube from this formula. And N2 by N1 equal to 0.75. N2 by N1 equal to 0.75. We know that torque is proportional to flux and armature current. This is the base formula. We know that. So we derive torque developed by a DC motor is proportional to flux and armature current. So therefore, T2 by T1 equal to phi 2 Ia2 by phi 1 Ia1. So this is proportional to, because it is a series motor. In series motor, flux is proportional to armature current. Flux is proportional to armature current because armature and field both are connected in series. Armature and field both are connected in series. So therefore, if flux is proportional to Ia2, so Ia2 into Ia2, Ia square. Ia1 into Ia1, Ia1 square. So therefore, torque is T2 by T1. So from these two relations, so Ia2 by Ia1 whole square equal to N2 by N1 whole square. So from this, we calculate Ia2. And then we calculate the resistance. We substitute that value to so substitute in back EMF equation, and then we get the solution. So I give answer for that one. So answer equal to for this 7.15 problem. So substitute in back EMF and then so this is the solution. So this is after calculating the armature current, substitute that into back EMF equation EB. So E2 equal to, note down this problem, E2 equal to V minus Ia2 into armature resistance plus external resistance that must be added in series with the motor because this is series motor. So from this, so V minus, we know that V value 500 volts minus Ia1 value 38.5 amperes. Here we get 38.97, and then from the relation E2 by E1 equal to E2 by E1 equal to, so N2 by N1 into phi 1 by phi 2. Phi 1 by phi 2. The speed is proportional to back EMF by flux. So you substitute this equation in this one, E2 equation, and we know that E1 value 470. So E2 by 470. In E2 we substitute this value, and this R is existing. We know that phi 1 and phi 2 relations, and then calculate R equal 6.455 ohms. 6.455 ohms. To substitute this voltage and this voltage 470 E2 by E1. E2 equal to substitute this equation E1 value 470 by N2 by N1. N2 by N1 means speed relation is given. So N2 equal 0.75 into N1. So that means it's 0.75 into 5 1 by 5 2. 5 1 by 5 2. So 5 1 by 5 2 is substituted with 38.97 by 60. That is I1 by I2. We know that I1 value 60 amperes. I2 value 5. Here we calculate 38.97. Replace 5 1 by 5 2 with I1 by I2. This 5 1 by 5 2 is replaced with I1 by I2. That is IA1 by IA1 by IA. Because series motor, in series motor, armature current is proportional to flux. Because both are connected in series. Both are connected in series. So that's why it is replaced with 5 1 by 5 2 is replaced with IA1 by IA. So IA1 value 60 amperes. Oh, sorry. IA1 by IA. So flux 5 1 is replaced with IA1. I2 is replaced with 5. So this is the resistance value inserted in this is the armature circuit. Next. So this problem is also based on series motor. 200 volts DC series motor runs at 1000 RPM. Motor runs at 1000 RPM. It takes 20 amperes. 20 amperes. Combined resistance of armature field. Combined resistance of armature and field is 0.4. Means series field resistance, armature resistance, total resistance equal to 0.4. Calculate the resistance to be inserted in series so as to reduce the speed to 800 RPM. Initial speed 1000 RPM. To reduce the speed, final speed 800 RPM. Assuming torque to vary as a square of the speed. Assuming torque to vary as the square of the speed. So torque is proportional to speed square. Given condition. Last case torque is proportional to n cube. Here torque is proportional to speed square. Linear magnetization current. Linear magnetization, linear unsaturation. Linear magnetization means unsaturated condition. Unsaturated condition. Two conditions are given. Unsaturated means flux is proportional to armature current. Series motor. Flux is proportional to armature current. So this is unsaturation. This is unsaturation condition. So this is the problem. So initially takes 20 amperes of current. So armature line current equal to armature current in series motor. So this is the 20 amperes. Speed 1000 RPM. N2 value also given second speed. So E1 equal to V minus IA RE. IA1 RE1. So this is equal to RE is also there. 20 minus 200 minus 20 into 0.4. So this is the back EMF first case. So in series motor, torque is proportional any motor, series motor or shunt motor, torque is proportional to flux and armature current. So in series motor, flux is proportional to armature current. So therefore torque is proportional to IA square. IA square in series motor. Torque is proportional to IA square. So therefore T2 by T1. T2 by T1 equal to IA2 by IA1 whole square. IA2 by IA1 whole square is the condition. Torque is proportional to IA square, IA2 by IA1 square. So torque varies as the square of the speed. So that means another condition, torque is proportional to speed square. Therefore, current square equal to speed square. So that means reference speed 800 rpm, initial speed 1000 rpm. So the ratio is calculated 800 by 1000 speed space. So therefore IA2 equal to 0.8 into IA1. So as given condition, IA2 equal to 0.8 into IA1. So that is 60 amperes. So then you calculate the back EMF in second case, E2 equal to E minus IA2 0.4 plus R value. That resistance is added in series with the water circuit. So this is equal to, this is the one equation. Now same equation 2 by equation 1. The speed is proportional to back EMF by flux. Speed is proportional to back EMF by flux. So E2 by E1 equal to N2 by N1. Here 5.1 by 5.2 I think. 5.1 by 5.2. So N1, N2 by N1 equal to EB2 by EB1. So fluxes are in reverse direction. Fluxes are in reverse direction. That is 5.1 by 5.2. 5.1 by 5.2. Therefore, E2 by E1 equal to N2 into 5.2. Okay, same right. 5.2 by 5.1 is say correct. 5.2 by 5.1 is correct. So 5.2 by 5.1. So N2 by 5.2 by N2 into 5.2 by N1 into 5.1. So 5A2 flux is proportional to armature current. Flux is proportional to armature current. So therefore, this flux is replaced with armature current. IA, IA2, IA2, IA1, IA1. So N2 by N1 equal to 800 by 1000. 800 by 1000 is value. 1000. IA1 value 16, IA2 value 16, 20 ratio. Then we calculate the external resistance inserted in the series with the motors. So IA2 by IA1 equal to 800 by 1000. Spares cancel out. Spare. IA2 by IA1 equal to that is 0.8%. In this manner, we calculate the problems on DC machines. If you have any doubts, only 72% numbers are there. Any doubts? Couple minutes wait చేయండి నేను అటెండెన్స్ తీసుకుంటాను.